Hi, today's video will be on the chapter Calorimetry and Latent Heat. Here also I have attempted to solve some of the selected numerical problems. Okay, so before starting solving the questions, let us now see what all are the important formulae that we have to see in this chapter. So we have to basically focus on two things mainly. One is called as the specific heat and second is called as the latent heat. So one is specific heat and second is the latent heat. Now this specific heat, or it is also called a specific heat capacity, it will come into picture when there is change in the temperature of the substance without having any change in its state. Okay, for example, if we have water, if its temperature is rising from, let us say, 20 degrees Celsius to 30 degrees Celsius, then what we have to use is specific heat. Okay, latent heat we'll discuss later. It will be used when there is change in the state of the substance without having any change in the temperature. Okay, so the formula that we use which is involving this specific heat is Q is equal to M into C into delta T. Okay, Q is the amount of heat which is given to the substance, M is the mass, delta T is the change in temperature, and C is the specific heat. So if we go to the definition of specific heat capacity of a body, it is the amount of heat required to increase the temperature of 1 kilogram of substance by 1 degree Celsius or by 1 Kelvin. Okay, therefore its unit is joule per kilogram per degree Celsius or joule per kilogram per degree Kelvin. Okay, so C is the specific heat capacity. Okay, in addition to this specific heat, we have simply what is called as the heat capacity. Okay, so this heat capacity is represented by C dash, and the relation between this C dash and C is C dash is equal to mass of the substance multiplied by its specific heat capacity. Okay, so the unit of C dash would be equal to simply joule per degree Celsius or joule per Kelvin. Okay, this is about our specific heat. Now what we have to see is the latent heat. So as I said earlier, latent heat would be involved when there is a change in the state of the substance without having any change in the temperature. Okay, so we represent this latent heat by L, and the formula that is there which involves this latent heat is Q is equal to M multiplied by L. Okay, so M is again the mass of the substance, Q is the amount of heat given, and L is the latent heat. Okay, now latent heat may be of different kinds. For example, if we have water, okay, so let us say we have water at 0 degree Celsius. If we want to convert it into ice at 0 degree Celsius, so what we have to take, okay, we have to take out the heat from that. Okay, so that amount of heat that is taken out from the water is called as a latent heat. Or suppose if we have ice at 0 degree Celsius, you want to convert it into water at 0 degree Celsius, then some of the heat is to be given to that, okay, in order to have the melting of the ice there. So that is called as the latent heat there. Its unit will be simply joule per kilogram. Okay, so the SI unit, fine, because there is no change in temperature here, therefore no temperature term is involved over here. So these are the three basic formula that we have to use for solving the numerical. One more thing that has to be kept in mind is the very important principle that is called as the principle of calorimetry. Okay, or it is also called as the principle of mixture, which is used in almost all the numericals. Okay, so what we have is the principle of mixture, or it is also called as the principle of calorimetry. Calorimetry means the measurement of heat. Okay, so for example, suppose if I mix two things, okay, two things, they may be liquid, they may be a liquid and a solid. Okay, but yes, we call it as the mixture. Okay, so whenever we mix two things which are at two different temperatures, then of course the body which is at higher temperature would be losing the heat, and the body which is at lower temperature, it would be gaining the heat. Okay, so in either of the conditions what we have, okay, the heat lost will always be equal to what? Heat gain. Okay, this is nothing but the other form of what is called as law of conservation of energy. Okay, so this heat lost is equal to the heat gained. That is, the cold body would be gaining the heat and the hot body would be losing the heat, but in any case what we have is the heat loss is equal to heat gain. So this is the summary of this chapter, particularly which will be involving the numerical part over there. Okay, so let us now start solving some questions. Okay, so the first question that we have is a certain amount of heat Q warms 1 gram of material A by 5 degrees Celsius and 1 gram of material B by 6 degrees Celsius. Which material has higher heat capacity? Okay, now in order to solve this question, you should be very clear with the definition of the specific heat capacity. Okay, so in this problem, same amount of heat is given, okay, and the mass is also same, but you can see that the temperature change is different over here. Okay, so this material A is getting raised by 5 degrees Celsius, temperature of this material B is getting raised by 6 degrees Celsius. You can see that there would be more amount of heat which is to be given for increasing the temperature of this body A. Okay, so what can be concluded is the specific heat capacity of this body A will be more as compared to the specific heat capacity of the body B, because giving the same amount of heat, its temperature rise is lower as compared to the body B. Okay, so this A will have more heat capacity as compared to B. Let us see the second question now. It is saying that 200 gram of hot water at 80 degrees Celsius is added to 300 gram of cold water at 10 degrees Celsius. Calculate the final temperature of the mixture of water. It is given that the heat taken by the container is negligible and the specific heat capacity of water is 4200 joule per kilogram per degree Celsius. Okay, now pause the video and just think which water would be losing the heat and which water would be gaining the heat. So you must have seen, okay, this is the water at more temperature, that is 80 degrees Celsius, so this would be losing the heat, and this is the cold water which is at 10 degrees Celsius, so it would be gaining the heat. Okay, now according to our principle of mixture, okay, what is the case? The heat lost by the water at 80 degrees Celsius would be equal to the heat gained by the cold water at 10 degrees Celsius. Okay, so what we have to find in this question is the common temperature, that is the final temperature of the mixture. So if I assume that the final temperature of the mixture is small t is the final temperature. Okay, so if I apply that principle of calorimetry in which heat loss is equal to heat gain, so what we can write here, heat lost by hot water would be equal to heat gained by the cold water, right? Formula would be the same for both the cases, that Q is equal to M into C into delta T. Okay, so if I take the hot water, okay, what I have is mass of hot water given to me is 300 gram. Okay, I am keeping it in gram only. Okay, because I have to equate and okay anyway, so that there will be cancelling if I'm okay, even if I convert that into kilograms. So I have M into C. Now C given to me is 4200, so it would be 300 into 4200 into delta T. Delta T is the change in temperature. So this hot water would be lowering down its temperature and it is coming to this temperature T. So the temperature difference would be how much? It would be equal to AT minus T. This AT minus T is the temperature difference there. Okay, and with the same token, if I see the heat gained by the cold water. Now cold water is given 300 gram. So 300, I'm so sorry. Okay, here the mass of hot water given to me is 200 gram, right? So it is 200 into 4200 into 300 is the mass of the cold water multiplied by the specific heat would remain the same, 4200 multiplied by the change in temperature. Now the temperature of this cold water would be rising, so the change in temperature, it would be equal to T minus 10. Okay, because this T would be greater than 10 of course, so it would be T minus 10. Fine. So I have to find the value of this T. A simple mathematical problems involving the linear equation. So what I have is this 4200 would be cancelling this 4200. What I left with is this 200 and 300, so both the zeros will get cancelled out. What I left with is 2 into AT minus T, okay, is equal to 3 into T minus 10. Okay, So you can just solve this for t. So 80 into 2, 160 minus 2t is equal to 3t minus 30. Okay, so if I bring it here, it would be 160 plus 30 is equal to 190, and 3t plus 2t is equal to 5t. What I have is this t is equal to 190 divided by 5. So 190 upon 5, if you solve, that would be 5 3s are 15, and the remainder is 4, and 5 8s are 40. So it would be 38 degrees Celsius. So the final temperature of the mixture, okay, which is given in this problem is 38 degrees Celsius. Okay, let us now see this question number 3. Now in this question, okay, let us read the question first. It is saying that a calorimeter of mass 50 gram and specific heat capacity 0.42, this is joule per gram per degree Celsius. It contains water at 20 degrees Celsius, okay, and a metal piece of mass 20 gram at 100 degrees Celsius is dropped into the calorimeter. Okay, so after stirring, the final temperature of the mixture is found to be 22 degrees Celsius. We have to find the mass of the water which was there in the calorimeter, and he is given as the specific heat of water and the specific heat of that substance. Okay, this metal piece is given to us, this 0.3 joule per gram per degree Celsius. Now you see that there are three things that are given in this question. One is the calorimeter itself, second is the water, and third is the metal piece. Okay, so nevertheless we have to use again that principle of mixture. Okay, so again pause the video and think which all quantities would be gaining the heat or which all would be losing the heat. Okay, just think. So you must have thought that, okay, this metal piece, okay, it is at 100 degrees Celsius, and the calorimeter which is containing water is at 20 degrees Celsius. So naturally calorimeter and water, they would be gaining the heat, and metal piece is going to lose the heat. Okay, so what we can write here is the heat gain. Okay, now two quantities or the two substances would be gaining the heat, that is heat would be gained by the calorimeter and water. Okay, so calorimeter and water, that would be gaining the heat, and the metal piece would be losing the heat. Okay, it would be equal to the heat lost by the metal piece. Okay, now in this question the final temperature of the mixture is given to us. Okay, that is this small t is given to us. You can see that that is equal to 22 degrees Celsius. Okay, so the heat gained by calorimeter and water, okay, we will find it by applying the same formula. Q is equal to mc delta T. So we have to take the mass of calorimeter, specific heat of calorimeter, and of course the change in temperature, plus the same formula for the water we will be using. Let us now calculate the total heat which is gained by the calorimeter and water. So if I want to write the heat gained by the calorimeter, okay, you can see that I can write mass of calorimeter, that is 50, multiplied by the specific heat of calorimeter, that is 0.42, multiplied by the change in temperature. Now initially the calorimeter and water, they were at 20 degrees Celsius, and the temperature is rising to 22 degrees Celsius. So there is a change of 2 degrees Celsius temperature. Okay, so this is the heat gained by the calorimeter plus the heat gained by water. Let us now write that. So heat gained by water is mass of water, okay, that is to be found out, okay, because we don't know. So let us assume it to be equal to m only. That is, m is the mass of water which is to be found out. Okay, multiplied by the specific heat of water, which is given to me 4.2, and again the change in temperature. Now change in temperature would be same 2. Okay, is 2 because calorimeter and water, they are having the same temperature initially, and the final temperature is 22. Okay, so this sum would be equal to the heat lost by the metal. Okay, so heat lost by metal, again the same formula, mc delta T. Mass of the metal piece given to me 20, multiplied by he has given me the specific heat of the metal piece. The Cm is the specific heat of metal piece, which is 0.3, and the change in temperature. Fine. So the metal piece was at 100 degrees Celsius initially, and finally it is coming to 22 degrees Celsius. There is loss in temperature, or the lowering of the temperature. So 100 minus 22, that would be equal to 78. Okay, now you can solve this. Okay, it is simple arithmetic result, and you can find the value of m. Okay, so if ever I try to solve, so I would have 50 into 2, 100 into 0.42 is 42, plus 4.2 into 2 is 8.4. It would be 8.4 into m, that is equal to 20 into 0.3 into 78. Okay, so 20 into 0.3 will be equal to 6 into 78. If I solve this, so it would be 468. So you solve it. Okay, bring this 42 here and this m. If you solve it, and then the answer would be 50.71 something gram. So this much is the mass of the this is the mass of the water that was there in the calorimeter initially. Let us see the fourth question now. Calculate the heat energy required to melt 10 kilogram of ice at 0 degree Celsius so as to form water at 0 degree Celsius. Now you can see that there is no change in the temperature. Okay, ice at 0 degree Celsius is to be converted into water at 0 degree Celsius. So what we have to use is a simple formula. Okay, this Q is equal to m into L. This L here is called a latent heat of fusion of the ice. Okay, because it is converting to from ice to the water. So it will simply apply Q is equal to m into L. Okay, then here the mass of the ice given to you 10 kilogram. Okay, and the specific latent heat of water, the ice is 334 kilojoule per kilogram. So you have to be very careful about the units over here. So it is in kilogram. Okay, it is in kilojoule per kilogram. So I have to convert this kilojoule to the joule first. So it would be 334 multiplied by 1000. 1000 will be written as 10 to the power 3 into joule per kilogram. So this kilogram cancel. What I left with is simply joule. Okay. So if I calculate the answer, my answer would be 334 into 10 to the power 4 joule. Okay. This is the answer for this. So why I took this question? Because here the value is not given to us in joule per kilogram but in kilojoule per kilogram. So in your examination you have to be very careful about the units in which the values are given. So you have to convert them accordingly. Yes, so this is question number 5 of this video. A refrigerator converts 100 gram of water at 20 degrees Celsius to ice at minus 10 degrees Celsius in 35 minutes. He is asking us the average rate of extraction in terms of watt. Okay, average rate of extraction means the amount of energy taken out per second by the refrigerator. That is the power of refrigerator. So we have to find it in watt. Okay, so we have to do the same thing, but here we have to apply both those formulas simultaneously. Okay, because what is initially given to us 100 gram of water at 20 degrees Celsius. So when refrigerator it starts extracting heat from that water, first of all the water at 20 degrees Celsius would be converting into water at 0 degrees Celsius. Then water at 0 degrees Celsius would be converting into ice at 0 degrees Celsius, and then ice at 0 degrees Celsius would be converting into ice at minus 10 degrees Celsius. So these are the three terms which would be involved in the solution of this numerical. Okay, so if we just see the steps in terms of numerical here, let's assume that the total amount of heat is Q. Okay, so what will happen in the first step? Okay, what will happen in the first step? Here the water at 20 degrees Celsius would be converting into water at 0 degrees Celsius. So for that I have to again use Q is equal to mc into delta T. What is the mass given to me? Mass given to me is 100 into what is the specific heat of water is 4.2 joule per gram per degree Celsius. So I will writing simply 4.2. Okay, multiplied by the change in temperature. Fine. So water was at 20 degrees Celsius. It is coming to 0 degrees Celsius. It would be 20 minus 0, that is equal to 20. Okay, plus now the water at 0 degree Celsius would be converting into ice at 0 degree Celsius. There is no change in temperature, so what is involved there? Q is equal to ml. Okay, so this latent heat of ice is given to us. Mass would remain the same, so it would be Q is equal to ml. So m is 100 multiplied by 336. Okay, this is 336. Now here ice at 0 degree Celsius reached. Now we have to convert that ice at 0 degree Celsius to ice at minus 10 degree Celsius. So again we would be using the formula Q is equal to mc into delta T, right? So that mc into delta T, mass would again be 100 into the specific heat of ice is given to us 2.1 multiplied by the change in temperature. Now the temperature initially it was 0, now it is changing to minus 10, so it would be 0 minus minus 10 is equal to 10. There would be a 10 degree fall in temperature of the ice now. So if you just add these three terms, what I left with is I would be having 100 into 4.2 into 20, that would be equal to 8400. Then I have 100 into 336, that is 33600. Then I have 100 into 2.1 into 10, that is equal to 2100, and the addition of these three terms would be 44100. So this much is the total amount of heat that is to be extracted by the refrigerator to convert water at 20 degree Celsius to ice at minus 10 degree Celsius. But he has given us time also. In 35 minutes it is to be done. So the time is equal to 35 minutes. So we have to convert it into seconds because the power is asked in watt. So 35 minutes. So 35 minutes in seconds, it would be equal to 2100 seconds. So my power would be equal to, that is the rate of extraction of heat. Okay, that is Q, that is energy divided by time. What I have is 44100 divided by 2100. So if I just do that, that would be equal to 21. Okay, simply this will be cancelled. So I have is 21 watt. So the power of the refrigerator, that is the average rate of extraction of the refrigerator in terms of watt, would be equal to 21. Fine. So the next question now is, I have been given 40 gram of water at 60 degrees Celsius is poured into a vessel containing 50 gram of water at 20 degrees Celsius. The final temperature recorded as 30 degrees Celsius. I have to calculate the thermal capacity of the vessel. Okay, not the specific heat capacity, but thermal capacity, that is C dash. So C dash is mass multiplied by the specific heat capacity of that vessel, that is to be found out. Okay, so again you can see that 40 gram of water is given to me at 60 degrees Celsius. Okay, it is poured into a vessel which is containing 50 gram of water at 20 degrees Celsius. Two type of waters are given to me, one at 60 degrees Celsius, second is 20 degrees Celsius. Now of course the vessel would also be at 20 degrees Celsius because it is containing water in it. Fine. So both the vessel and the water at 20 degrees Celsius would be gaining the heat, and this water at 60 degrees Celsius would be losing the heat. Okay, so we apply the same principle, that is principle of mixture. What I have here is heat lost. Okay, the heat lost by hot water would be equal to heat gained. Okay, now heat gained by cold water. Cold means the water which is at 20 degrees Celsius, by cold water and the vessel. So plus vessel. Heat gained by cold water and the vessel. So what is the heat lost by the hot water? Again the same formula, Q is equal to m into C into delta T. The same formula we are using. So it is mass is 40. Okay. Then specific heat of water is 4.2, and the change in temperature. Now the final temperature is 30 degrees Celsius. Initially it was 60, but I have is 60 minus 30, that is equal to 30. So this 30 degrees Celsius is a change in temperature, that is equal to the heat gained by the cold water. So if I see this water, the mass of the cold water is 50 gram, multiplied by the specific heat would remain the same, 4.2, multiplied by the change in temperature. Now it is 60 degree, sorry, it was 20 degrees Celsius and now it is becoming 30. So it is raising its temperature by 10 degrees Celsius. So it is 30 minus 20, that is equal to 10. Okay, plus the same formula for the vessel. Okay, because now mass of the vessel is not given to me. Let us assume it equal to mv. Suppose mv is the mass of the vessel, multiplied by, let us see, this Cv is the specific heat capacity of the vessel, multiplied by the change in temperature, right? So the change in temperature would be the same, 30 minus 20, that is equal to 10, because water at 20 degrees Celsius is contained in the vessel itself. So of course the vessel would also be gaining the same temperature of 10 degrees Celsius. Now if you identify this term, mv into Cv, Cv is the specific heat capacity of the vessel, mv is the mass of the vessel. So the product of these two terms is giving me nothing but the heat capacity or the thermal capacity of the vessel, whose value is to be calculated here. Okay, so let us now solve this. What is 40 into 4.2 into 30 is giving me 5040. Then 50 into 4.2 into 10 is giving me again 2100, plus this term I am writing as C dash V. C dash V is the thermal capacity of the vessel multiplied by 10. Okay, so if I find this value of Cv dash, okay, you can calculate, it would be 5040 minus 2100 divided by 10, so it would be equal to 294. Unit would be equal to joule per gram, because we have taken all the masses in gram only. Okay, so its unit would be joule per gram. Correction, joule per degree Celsius. Fine. So the heat capacity or the thermal capacity of that vessel would be 294 joule per degree Celsius, right? This question number 7. This question I have taken from the sample paper of second semester ICSE 2022. It is saying that there is a graph given to us. So the diagram below shows a cooling curve for 200 gram of water. The heat is extracted at the rate of 100 joule per second, that is in 1 second 100 joule of energy is being taken out from the substance. We have to answer the question. Number 1, we have to calculate the specific heat capacity of the water, and number 2, we have to find the heat released in the region BC. Okay, so here on x-axis the time in given in second, and on y-axis we have been given the temperature in degree Celsius. Okay, so you can see that from point A to point B the temperature of the substance is decreasing, and from point B to C there is no change in the temperature. So you can see that it corresponds to the change in the state of the substance, and it corresponds to the temperature change. There is no change in the state of the substance as such. Okay, so let us now see the first part of this question. It is saying me calculate specific heat capacity of the water. Okay, now you can see that I have to apply the same formula, right? That Q is equal to M into C into delta T. Okay, now you can see that the time that the body is taking to go from point A to point B. So if you see the time at point A, the time given to me is 0. Okay, these are the coordinates. 0, 0 is the origin, so time is 0. And at point B, okay, when the body is reaching to this point B, the time that it has taken is 640 seconds. Okay, so in 1 second, okay, 100 joule of energy is getting extracted. So in 640 seconds, how much energy would be extracted? It would be equal to 640 multiplied by 100. There is 640 into 100 is the total amount of heat that is getting extracted from the body when it is coming from point A to point B, right? So the total amount of heat would be 640 into 100, that is equal to mass of the water given to me is 200. C is to be calculated, and this delta T. What is the change in temperature? If you see, it was initially at 80 degrees Celsius, now it is reaching to 0 degrees Celsius. So it would be 80 minus 0, that is equal to 80. Okay, so you can find the value of C from here. So my C would be equal to 640 into 100 divided by 200 multiplied by 80. Okay, so you do this. Okay, your answer would be simply equal to 4. It would be 4 joule per gram per degree Celsius, right? This is the answer of the part A, that is the specific heat capacity of the water. In the second part, he is asking the heat released in the region BC. Okay, so heat released here in the region BC, it can simply be calculated by using the same result. Here I am given 100 joule per second. So again, in 1 second 100 joule of heat is extracted. So if you see that the time that the body is taking to go from this point B to point C, it would be how much? 1312 minus 640. Okay, this is the time taken to go from point B to point C, and in 1 second the heat extracted is 100. So in this much time would be equal to multiplied by 100. So if you do this, it would be 1312 minus 640, that is equal to 672, and if you multiply it by 100 again, so what I left with is 67,200 joule. So this is the total amount of heat that is extracted from the body, okay, when it is going from the point B to the point C. So this is an important question. Okay, it is given also there in your sample paper. Fine. So here we have come to the last question of the session. It is saying that calculate the power of an electric heater which can convert 2 kg of water at 30 degrees Celsius to steam at 100 degrees Celsius in 20 minutes. Okay, so water is to be converted to steam. Okay, so again, initially the water given to us is at 30 degrees Celsius. So when we give heat, its temperature would be changing, that is, it will be rising. So first of all, we have to calculate the amount of heat which is required to raise the temperature of water from 30 degrees Celsius to 100 degrees Celsius. Then further amount of heat is to be given to convert the water at 100 degrees Celsius to the steam at 100 degrees Celsius. And for this whole process, the time that is given to us is the 20 minutes. Okay, so we have to calculate the power of that heater which is doing this process. Okay, first of all, calculate the total heat that is to be given to the water. Okay, so again I will be using Q is equal to that formula again, mc delta T plus m into L. Fine. So same formula we are using. So what is mass of water given? Mass of water given to us is 2 kg. Okay, multiplied by the specific heat of water that is given to me is 4180. Again take care of the units. Now 4180 is joule per kilogram per degree Celsius, and multiplied by the change in temperature. So initially it was 30, that is going to 100. So the change in temperature would be 100 minus 30, that is equal to 70. Okay, this is the amount of heat, okay, which is moving the water from 30 degrees Celsius to 100 degrees Celsius. Now the further provision of heat would be changing the water at 100 degrees Celsius to steam at 100 degrees Celsius. So the mass would remain the same, mass would be equal to 2, and the specific heat capacity of the the latent heat of vaporization of water that is given to me is 22.68 into 10 to the power 5. It is joule per kilogram. This is the latent heat of vaporization of water, that is the amount of heat required to convert water at 100 degrees Celsius to steam at 100 degrees Celsius. The temperature would remain the same. So if I just simply calculate the total amount of heat required, okay, you also do this. So if I calculate it, it would be around 5121200 joule. Okay, so this much is the amount of heat you see required to be given, okay, to convert the water at 30 degrees Celsius to the steam at 100 degrees Celsius. Now time given to me is 20 minutes, okay, time given to me is 20 minutes. 20 minutes is to be converted into seconds, so 20 multiplied by 60, okay, that would be 1200 seconds. So again you can see that my power is equal to amount of heat per unit time, okay, so time, but heat is again 5121200 divided by 1200. So I would be losing these zeros from here. If I calculate it, okay, so I'm just writing the answer in kilowatt, okay, you also solve it, it would be around 4.267 kilowatt, okay, that is 4.267 10 to the power 3 watt, okay. So this is all about this video, okay. You try to solve more problem, okay. If at all you are facing anything, just let me drop a message to this mail or this phone number. Thank you. God bless you all.